By the way, so the handout should be in the Google Classroom now. I really do apologize for it being very late, but it turned out it was 18 pages. So it did take a while to write up, and the PDF should be there. There are around five, I think five exactly problems at the end, which there aren't really any linked list or array list problems, but there are a lot of like set and hash map problems. So yeah, let's go. This is week 4, and we're gonna do graphs. Well, thank you all for staying till week 4. I know it's been quite a few weeks. The past 3 times might have been a bit challenging, but I'm sorry to say that this might be more challenging. Just a quick recap of last time. We talked about advanced data structures, and data structures are collections of data, and we categorized it into linear and non-linear data structures. It depends on the type of data structure that you want to use, depends on what the problem is. Now, you can store primitives as well as custom classes or classes that you create yourself, but especially, or actually only when you're considering like sorting, such as for priority queues or for like arrays and array lists, you have to implement comparable, which we'll see again this time. Here's just the graphic organizer, I think that's the name, yeah, that I showed last time. Again, very good. Array list is not on here because it's just a type of array. We refer to tables as maps, and then graphs is the thing we left out last time, which we'll be talking about this time. Now, the reason we left out graphs, as I said last time, was because there's just so many things that you can do with graphs, and there's so many different types of graphs, to the point where it's kind of absurd to learn all of it. So we'll just be focusing on the types of graphs that you'll actually need to know for USACO. So quick disclaimer, this is not everything about graphs. Now, the simple definition of a graph is a collection of vertices, V, and edges, E. For our standard graphs, each edge connects 2 vertices, V1 and V2. So I drew an example here of a graph. Each edge, as you notice, connects 2 vertices. These vertices are circles. There can exist multiple edges between vertices like this. And there can be these things called self-loops. Self-loops means the edge connects the vertex back to itself. So V1 would be equal to V2. Also, edges or vertices don't always have to be connected with the other vertices. So this is a vertex that's disconnected from the rest. Here's a definition that I actually left out from the presentation, but I think it might be pretty important to know. Connected component means a connected component is a set of vertices and edges where each vertex can be reached or you can go from any vertex to any other vertex in the connected component. So this group of 6 vertices are in one connected component because I can go from any vertex to any other vertex. And then this vertex down here would be in a connected component by itself. Yep, I think that's it for this slide. You'll often see undirected graphs and directed graphs, and they're 2 different things. Undirected graphs are the normal things that we might be used to, where edges connect 2 ways. So we can think of this as a road, kind of. This is, let's say, a city, or let's say a neighborhood. That's another neighborhood. This edge in an undirected graph means that I can go from one neighborhood to the other, and from this neighborhood to back to the first one. As opposed to an undirected graph, a directed graph has one-way edges, which means that edges point from one vertex to the other. And sometimes if you have like 2 undirected edges, then, if you have two directed edges going in the opposite directions, then it acts like a normal edge. But most of the time you'll see like this. This means that the top vertex can reach the bottom one, but the bottom one can't reach the top one. So here the definition of connected component actually gets a bit harder, because previously all of these were connected. But if I somehow if I drew arrows on so that these became one-way streets instead of two-way streets, then, for example, this vertex, all the roads that go to this vertex or connected to it go into it, so you can't go out of it. That's just something that you might want to watch out for. Yeah, I'm sorry. It just told me that my connection's a bit spotty. If I ever cut out, just tell me in the chat. But thank you. So weighted graph is something we'll see later on today. And it's a graph where edges have weights. These weights usually correspond to a cost of some sort. Maybe it's like, maybe these are like telephone, or these are all people. They're messengers and they want to deliver a message. The cost to deliver a message from this person to that person would be $2. This would be $1. That would be $10. So we would want to avoid that. Other times we can think of these edge weights as distances, in which case we can think of like these as cities and these as roads. And then these edges are like roads between the cities, and they have lengths. So maybe an example problem would be like, find the shortest distance between two cities if you have to go along roads. Edges can also have weights if you're using a directed graph. But that's just kind of weird. If we're talking about distance, so usually if it's a directed graph that has weights, we're probably talking about like maybe like the messenger thing again. One messenger can talk to the other, but the other can't talk to you. A spanning tree is it's a subset of the graph, and it's a group of vertices and edges such that every vertex was visited. So if we go back here, we still have these 6 vertices, but there are no cycles. I realize that the definition of cycle is left out, but I think y'all can tell that this is a cycle because there are 2 ways to get from any point to another point in the cycle. I can either go like that or I can go like that. So that's a cycle. Hey guys, really sorry. My Wi-Fi just went out. Thank you for staying, for all of you who did. Let me bring back the PowerPoint. I think I'll have to share on this computer, just because the other one hasn't connected to the hotspot yet. Okay. So very sorry about that. And while I'm talking, I'll try to connect to my other computer. Is this screen showing up for y'all now? Okay, thank you. Okay, spanning tree, we did that. Harder graph theory, I just want to talk about some of the things that might show up There's something called hypergraphs where edges can connect like multiple vertices instead of just vertices. So that's really crazy. Sine graphs, kind of like directed, but a bit different. And then this Laplacian matrix, random matrices that might or might not show up in college classes. These are things, I just wanted to include them in case like you guys have nothing to do over the summer or at some point, maybe during school, and just want to search it up. USACO will basically only use everything that we just talked about. Normal graphs, a directed and undirected graph, and spanning trees, and sometimes like connected components. Now, one of the problems is how do we represent a graph in code? So we could either use an adjacency matrix or something called an adjacency list. An adjacency matrix is a V by V matrix where this represents the size of the number of vertices, and the cell at position ij is 1 if there's an edge from vertex I to vertex j, and it's 0 otherwise. 0 means there's no edge from I to j. So this, you might notice that this means that for undirected graphs, like this, this means that 0, 1, which is our row 0, column 1, will be equal to row 1, column 0, because these graphs go both ways. This isn't necessarily true for directed graphs though, because there's one-way roads instead of two-way roads. So here would be the adjacency matrix for an undirected graph where the colors correspond to the edges, or these numbers correspond, what am I saying? The colors like match and they look nice. And you can tell that this matrix is symmetrical across the diagonal. So for example, if I go to row 1, column 2, this means, is there an edge going from vertex 1 to vertex 2? And if we look at the graph, there's no direct or immediate edge, so that's a 0. Now here's a directed graph with one-way edges. And now this means, this 1 means that vertex 0 can go to vertex 1, or the edge goes from 0 to 1. So it would be this, in this direction. And the others are similar. I'm a bit concerned for my bandwidth, so I actually might just use Eclipse on this computer to show stuff. So our other choice to represent a graph is the adjacency list. And this still has V rows, or size of V rows, but the number of columns varies. It's not going to be uniform like this. Oops. So we represent an adjacency list as an array of array lists, where the ith array stores an array list for each I from 0 to n-1, and then this array list stores all the vertices that the vertex at I can lead to. So I think that makes more sense if I use this example. This again is the directed graph. 0 can go to 1, 2, and 3. So the array list at ADJ of 0 will have 3 elements, 1, 2, 3. 1 just goes to 0, so it only has 1 element, and so on. Now this is actually a bit easier than this. There's less elements. In this case, there's only 8 things that we have to actually store, whereas here we had 16 ones and zeros that we had to store. The same works for, we can still do an adjacency list for a directed graph. It's just a bit trickier. And when you're given the input, you have to be a bit more careful about like how the input is formatted. Like, is the first number leading to the second number, or is the second number leading to the first number? Usually our convention is like 0 would lead to 1 and 2, which means that 1 and 2 are in the array list at index position 0 of our adjacency list, right? 0 would go to 1, and then 0 would go to 2. It's not color coded here, but I think it makes sense. I will point out that it's just coincidence that 1, 2, 3, and 0 each show up once here. Normally, this doesn't have to happen. So it just happened to be this example where 1, 2, 3, and 0 each show up once. So let's analyze the differences between the matrix and the list. For the matrix, it's useful if we're looking for the existence of an edge between 2 vertices. So it's good for lookups. If I go back here, it's very easy to go to some row and then some column and see if there's an edge between them, as opposed to in the adjacency list. If I want to see if there's an edge between, let's say 0 and 3, I would go to 0, then I have to go 1 by 1 and check each element in the array list to see if it's equal to 3. So worst case, if this list, if 0 is connected to a bunch of edges, then worst case, I have to go through every single vertex that it's connected to, and 3 is at the very end somehow. And that's where the adjacency matrix would be much better. However, adjacency lists are good for traversing. And by traversing, I mean going through edges. So like, let's say I wanted to move through the graph. And I only want to know like where 0 can lead to. So 0 can lead to 1 and 2. So this is great. I have 1 and 2 right here. That's all I need. I don't need to know that 0 doesn't go to 3. Whereas if I use an adjacency matrix to traverse, I have to still go through the zeros, even though the zeros don't matter in this case. All I care about is the ones, but then I still have to make sure that I'm going through all the ones, and I have to go through an entire row just to find all the ones. So in general, if there are a few edges, then adjacency lists are good. If like there's a bunch of edges, a bunch as in the graph is almost complete, like there's edges between every pair of vertices, then our adjacency list is actually kind of gonna look like the adjacency matrix. In which case, either using the adjacency matrix or the list, or they're both pretty bad. So I would still go to the adjacency list for traversal. This isn't something really graph related or graph theory related, but for most of these problems, we'll want to have a visited array. So it's going to be a Boolean array of size for each vertex. So size of the vertices. And the ith element of the visited array tells us whether or not we visited that vertex. And we'll see why we need this coming up now. So are there any questions so far about graph definitions and all that? I'll give maybe like 1 minute just so I can connect to a hotspot. Okay, looks like there were no questions. Let me pull up the presentation on this computer first, join the Zoom. Okay, should be a few seconds. Okay, there we go. This is much better. Lesson 4. And now we're on breadth first search, our first graph algorithm. So an overview of breadth first search, or BFS, is we traverse a tree or a graph starting at some arbitrary vertex, and we traverse it layer by layer. Elements are in the same layer if they have the same distance from our arbitrary starting vertex. So like 2, 3, and 4 are each one edge away, which means in our BFS, we would first go to 1, then 2, 3, 4, then 5, 6, 7, 8, 9, 10, 11, 12. Oh, oops, okay. So this is a tree. And BFS is usually used for trees, but sometimes we can also use it for graphs. There's just a bit more like nuance to the code. Right now, I'm trying to look for my stylus, which is not appearing. Oh, there we go. For a graph, pull up our best whiteboard, the best whiteboard out there, paint. Let's say I have a graph like this. And we can tell it's not a tree because there are cycles. I think I should have pointed this out earlier, but trees are actually special types of graphs. Trees are graphs without any cycles. And we saw a special type of a tree, which was the spanning tree, that visits every vertex. But trees are graphs with no cycles. The tree that we talk about as a data structure, though, is a bit different because that acts more like a linked list than a graph, and we store it more. We write it as a class instead of a bunch of vertices and nodes. Sorry, a bunch of vertices and edges. We have like we have a bunch of children nodes and a parent node for trees. So if I decided to pick, let's say this vertex as my start, I'm just gonna number it like that. My BFS would go to every vertex that's, I'd start at like the closest vertices basically. So I might go here, then I'll go here, then I'll go here. And I kind of followed like a top to down pattern, so I'll follow that. Next, I'm looking for things 2 away. And to look for things that are 2 away from my start, I can look at things that are 1 away from the things I visited. And now I would start here because that's, I want to follow that order. And I would look at all the edges that lead away from 2. And I'll look at the top one first. So here's the top one. I'll number 5. Now consider the this one down here, vertex 3. I've already been there, so I won't renumber it. And now I've exhausted all the edges coming out of 2, which means I'll move to 3. So vertex 3, up here, there's 5, but I've already been there, so I'll go down. Here is vertex 6. That's how I'm gonna number it. And then I go back to 5 because that's the first vertex that I haven't. Oh, technically I would go to 4. 4 only has 1 going out of it, but I've already numbered 6. So I'm done with 1, done with 2, done with 3, done with 4. Now I go to the smallest vertex that hasn't been taken care of yet. Well, 5 goes to this vertex, so I'll call it 7. And now I'm done with 5. 6, I'm already done with because it doesn't go anywhere. 7 would go to 8, and then it would also go to 9. So I'm done with 7, and then 8 doesn't go anywhere, 9 doesn't go anywhere. So this is how I would conduct a breadth first search on a graph. Now it might look a bit more like the picture from earlier if I kind of rotate this diagram. So 1 would be up here, then 2, 3, 4. Oh, oops. 4, 5, 6, 7, 8, 9. And you can see that even though this is kind of reversed, I still go through each row before moving on to the next row. Okay. And here's something from last time that we can actually use. To implement a BFS, we want to use a queue. And the reason is, before I was mentioning, take the first thing that we haven't dealt with yet. And now this sounds like, or take the first thing that we haven't dealt with yet and deal with it. This sounds a lot like FIFO, which is first in, first out. Whatever goes into our queue first gets dealt with first. So now we're going to look at the code to write a BFS. But before that, are there any questions about how a BFS works? I guess conceptually. Okay. Hopefully that means no questions. Either that or I'm cutting out again. I'm just talking to a blank screen. So we're gonna do a BFS. Below here, I've actually, oh, oops, my gosh, my mouse. Here's like the input that we might be given. And I'll make a comment for this. Java multi-line comments are just /* and then close with /*, */. So my first number that will be given is the number of vertices, which I'll call n. Then we'll be given the number of edges, which is called e. And then for the next e lines, each pair describes an edge between vertex 1 and vertex 2. So here, this would mean I have 4 vertices, 4 edges. And for the next 4 lines, each line corresponds to an edge. So vertex 0 and 1 would be connected. 0 and 2, 0 and 3, 2 and 3 would be connected. So we'll start by making a scanner to scan in this data. Now, this isn't really necessary. You could like hard code your stuff, but if you want to like test your program out more, it's helpful to use a scanner so you can like input whatever data you want instead of having to like hard code it when you make the adjacency list. So we want to read this from the console. So we'll create a scanner from system.in. Doesn't know what a scanner is, so I'm going to be lazy and import everything in util, which is all we need. Now, our first integer that we're given is n. So that, and then the next integer that we're given is the number of edges. By the way, I'm kind of styling this like as the format that USACO would give you your data. They like to do it this way where the edge pairs, or sorry, the vertex pairs are separated by spaces. And then the first line tells you like the number of vertices or edges or whatever information you're given. Since we're going to be traversing, which is what a BFS is, we want to use an adjacency list. So here's how we make it. Earlier, I said it's an array of array lists. So this would be the outer one. So it's an array. And the data type that the array is storing is array list. Integer, I'm doing integer because these vertices are going to be represented by their, I guess, indices. So like vertex 0 would be 0, which is an integer. So I just want to initialize this. Now the problem here is I can't actually like do that or do that. All that doesn't work. I have to do it this way. And there's really no way to avoid this error, which says unchecked conversion. I'll say, I don't think I've ever used the alternative to this method, which is, okay, I guess there's two alternatives. One is you use an adjacency matrix, which will not work, which will not run in time if you're doing USACO problems for most of them. The alternative is, I'll comment this. We make an array list of array lists. And if we think of array lists as arrays, this is kind of just saying like, this is a modifiable size array by a modifiable size array. So it's like a 2D array that can change size, either in the row dimension or in the column dimension. So this is the alternative, and you won't actually get an error message. But I like it this way because I like array access more than the array list access, which is like .get. It's just kind of preference. Also, this makes more sense because you can't change the number of vertices you have. You're always like, every vertex is going to have an array list that corresponds to it. But the array list size for each vertex may be different. That's why it's an array list and not an array. But you still have n rows always. That's why I like to use the array. Technically, when I do this, I haven't yet created the array list inside of the adjacency list. So now I go through and say make an array list at each index. And I want it to be an integer. So that would be the code for setting up the adjacency list. At this point, I haven't read in any data. So my adjacency list would kind of look like this. Just empty array list, but 4 of them for each vertex. So now I want to go ahead and start reading data. I think during week 2, I said something where you have to like do fn.readLine or next line, I think. Yeah, fn.nextLine to move to next line. I learned today about that you don't actually have to do that. And the reason I thought we had to was because I usually don't use scanner. I use something called buffered reader and string tokenizer. These things are a lot more complicated to write out, but they work a bit faster than scanner. So if you have the time and you want to like memorize how to work with these, and they do the same thing as scanner. They're just a bit faster, but harder to write. If you want to learn that, I think it's definitely worth it. Anyways, now we want to go through the next E lines and update our adjacency list. So at each line, I want to read in the two numbers in the line. I'll call it V1 and V2. And in the problem statement, I didn't say this, but let's just say it's a directed graph. It's an undirected graph. All right, so, I guess we're not done yet. To say that V1 goes to V2, I access the array, the list for V1, and then add V2 to it. Now I would do the same thing for V2. Okay. So this is kind of like getting our adjacency list set up. So given that, now our BFS is we start at some vertex and then go through the graph using the BFS. Our first step is to construct a visited array, which will be Boolean because this tells us whether or not we visited the array, and that just has to be true or false. So we want n entries for each of the vertices. And now we're given some start vertex. So later on, I'll actually update this input so that there's an extra line after this that tells us what vertex we want to start at. At this point, we can actually see if our program works. So I'll run this. Get rid of that. That was an error for something else. Don't worry about it. And we'll just say we want to start at vertex 0. Okay. Oh, it's running the other one. This is the completed version. I don't want to do that. Let me delete this. Okay, I don't know. Okay, there we go. And we want to start at 0. So it doesn't do anything, but we didn't tell it to do anything, which is good. There's no error messages, which means we read in everything correctly. So here's our pseudocode. We have the visited array. Everything starts off as false because we haven't visited anything yet. Now we're given a starting vertex S. And we can say, oh, okay, so we start there, which means we visit that. So we set that to be true. Now we make a queue, which is a linked list, or that's how we implement it in Java. And we add S to it. And adding S means that we want to deal with S. And then while this queue is not empty, print out whatever is in it, or print out the first element. So consider the first element, pull it out, and print it out. Now print this, we want to replace this with like whatever action you want to do. Maybe it's like add it to or multiply it to some number. But we want to do this in the BFS order. I don't know. In this case, we'll just print it. And then every vertex that's adjacent to this, to the pulled vertex, if it hasn't been visited before, we're going to add it to the queue. So there's kind of like a recursive algorithm here. And if I go back here, let's say, looks like this. This is my start. So I would add this to my queue and I pull it out because it's the only element in there and it went in first. Then I would add these elements into the queue. And notice the order that I added them in. I added this one, then that one, then that one. Then, so this is already out of the queue. I don't have to worry about it anymore. And I printed this out earlier. We call this A, B, C. Then I would go to A and look at whatever this leads to. maybe 1, 2. Or I'd take out A from the queue. So now it's not in the queue and print it out. And then add 1 and 2 to the queue. Oh gosh, maybe I should have a running queue. So my queue looked like this at first. Then I deleted this, added A, B, C to the queue. Then I deleted A and added 1 and 2 to the queue. Now I look at the first element here, which is B, and add whatever this leads to the queue. Let's say 3. And then get rid of B. And then look at C, add 4 to the queue. Get rid of C. And this recursive, using this recursive method, I first go through my top layer, then my next layer, then the layer after that. Okay, so going back to the code, we have our visited array, and we want to set visited of S to be true. And I'll make our queue, which is a linked list, because Java doesn't have a queue. I'll call it queue to make it clear that it's acting as our queue. I don't know what's going on. Okay, that's weird. It's been missing. Just gonna ignore it because I don't think there's anything wrong with it so far. So we imported util.star, so linked list should be there. Now we add S to the queue, so queue.add S. All right, so there is something wrong. I have no idea what it is. Let me go back here and copy whatever. Oh, wow. I have a new because it's an object that we're creating. It's a new object. Okay, that's bad. And I add queue to the, I add S to the queue, and while the queue is not empty. Alternatively, you could do like while size is not equal to 0. I want to pull whatever's at the top. I'll say T because it's temporary, T for temporary, and queue.pull. Now, I want to go through all the vertices that are next to Q, next to T. So for each vertex next to T, this is the list from the adjacency list of like all the vertices that T goes to. So for each vertex in this list, if I've already visited, then don't do anything. So if I haven't visited this vertex, then I want to add it to the queue. And I want to say that now I visited it. Oh, oops, visited B. Okay. Down here, this is like what we would be doing with our program. So everything besides this line that I'm typing right now is like part of a standard BFS. This is what we do to like the elements that we encounter as we go across the BFS. In this case, we just want to print it out just to see that it's working. Okay, so Control V, and then start at 0. If you're wondering, the graph that this is referring to is this one. 4 vertices, and then 0, 1, 0, 2, 0, 3 are connected, and 2, 3 is connected. So this would go through 0, then go through 1, 2, and 3. And it's kind of a bad example because I'm actually, 0 is actually connected to everything, which means that it's just gonna, there's not another level past the first level. But I can guarantee you that this code works if we decide to make a bigger graph with more edges and more vertices and more layers. Okay, so this was the BFS. Here's the thing. I'll copy that. Let's go back here. Now DFS. DFS is pretty similar to BFS. We're also traversing it and we want to reach every element. The only difference is instead of going through layer by layer, we start at some vertex, but then we go through we go along a branch for as long as possible. And once we can't go any longer, we backtrack to some vertex where we can go to another branch, and then backtrack and keep going like that. So it's also recursive in nature. The difference is like for BFS, if your target, let's say you're looking for a value, if your target is like all the way down here, then you're actually out of luck because you'll have to go through every single vertex above it before you reach the final row. So it's going to take a long time. For DFS though, let's say this vertex was the thing I was looking for. It would only take 3 iterations for me to reach there because I would go along this branch as long as possible, and then I would reach 4. This numbering, again, like earlier, tells you the order in which the vertices will be visited. So this would take 3 iterations instead of like 1, 2, 3, 4, 5, 6, 7, 8 iterations. And the way we do this is stack, because we can think of like putting a vertex on top as like, okay, or we think of it as a stack because of its last in, first out behavior. And if 1 is the last thing we put in, then we deal with it first. Then we add 2, or we add 8, 7, and 2. 2 was the thing we put in last, so we want to deal with it first. So we add in 6 and 3. 3 was the thing that we added last, so we go to 4. And we just repeat that pattern. I know the numbering's a bit crazy. And you'll notice that the pseudocode actually looks a lot like the BFS pseudocode. We have the same things, except this time we're using a stack. The terminology is a bit different, pop and push instead of pull and add. And it's really that easy to go from BFS to DFS in code as well. I just make a class called DFS, copy it over, change the class name, and let's see, everywhere where we had the queue, we just replaced that with the stack. And like before, we have to change the terminology. So there's that. For some reason, the like import java.star thing, if you copy it over, it's gonna like get rid of that and then import the classes separately. So that's why I didn't know stack, because earlier I didn't use stack and it just didn't create the import statement. But add is the same. Pull, I just want to replace with pop. And that's it. We just made a DFS, or we made the program for conducting a DFS. And if we run this, it's going to look a lot, or it's going to be the same exact output. But if we had, again, like a deeper graph, a more complex graph, then it would look different. Okay, wow, we don't have a lot of time. That's BFS and DFS. Shortest path problem, something you'll see a lot in USACO. And we use Dijkstra's algorithm. So the problem statement is given a weighted graph where edges have weights or costs, and you're given a starting vertex, let's say 0, find the shortest path from the starting vertex to all the other vertices. So this is the famous example on Geeks for Geeks. You might have seen this diagram before, but 0 would be our starting, and then these edges all have weights on them. So for example, the best way to reach 1 would be to go along this edge, 0, 1, because all other paths may be like this one going from 0 to 7, then from 7 to 1 would take 19, but this would only take 4. So obviously to go from 0 to 1, I want to do 4. I want to just go along this edge. Now that I've determined that the shortest path from 0 to 1 is 4, I can now look at, like, I can think of these things as settled vertices. These vertices are settled because I have I've determined the shortest path to them. So it makes sense that I've settled this one because the shortest path from 0 to 1 is 4. Well, I've settled 0 as well because the shortest path from itself to itself is 0. And now I can look at the shortest edge that goes from my settled vertices. In this case, I actually want to draw this out. So it looked like this: 4, 8, 8, 11, and other stuff. So I've settled this. I've settled that. This is vertex 0 and vertex 1. I want to have an array that tells me the shortest distance, so my dist array. And at the 0 index, I would have 0. At the 1 index, now that I've settled it, it has 4. And then now we look at the shortest edge that goes from, or actually no, the shortest path. Now the shortest, kind of the shortest like distance there is that's worthy of consideration. And that includes the distance from 0 to this place. And let's say there's another edge like that, the distance from 0 to that place and the distance from 0 to that place, because these are all adjacent to vertices that I've settled. This one is adjacent to that one to 0. This one's adjacent to vertex 1, and then this one's adjacent to vertex 1 as well. And then out of these 3 big ones that that are being considered, I want to choose the smallest one. And when I choose the smallest one, I know that it's settled because it's really the only thing that, like, it's the smallest, it's the best thing that can be settled. It's kind of hard to explain actually, but essentially, like, I think maybe writing the code out will be a bit better. Let me get rid of this code. For the sake of time, I'm not gonna make a new class. And oh gosh, this is not gonna finish in time. How about this? I'll put the code on the handout like I usually do, and I'll add some more steps this time so that, like, the steps hopefully make a lot of sense, just because we only have 5 minutes. But Dijkstra is a great term to know. It's a great term to know because it shows up in coding interviews and USACO a lot. But in USACO, there's usually more complex things. Maybe there's like 2 different edge weights. Maybe there's like a billion on each edge, something like that, weird stuff. Anyways, our approach consisted of having like a settled set of vertices, which I was kind of talking about. This set like tells us which vertices have been settled. A distance array, which tells us the shortest distance from the starting vertex to each settled vertex. And if and for those that are not settled, we just set it to like integer.max value to like tell ourselves that, oh, we haven't actually settled this yet. and the priority queue, because at each step, we look at the shortest path that hasn't been settled yet. So the easiest way to do that is to have a priority queue, which sorts stuff for us. In Java, it would be a min heap. So we can have like, it gives us the minimum edge or the minimum length path. Now, the final thing I wanted to talk about, which I now realize there's no time to write the code for, is the minimum spanning tree problem. And there's two algorithms for this. Now, like before, spanning trees of a graph are trees that visit every vertex. This is a spanning tree of a graph with 5 vertices. And we're given a weighted graph. Otherwise, there's no concept of like a minimum spanning tree. And now we're trying to find the graph with like the least total sum, or sorry, the spanning tree with the least total sum. Prim's algorithm is a greedy algorithm. And you start with some node. It doesn't actually matter what node there is. And in this problem, there's actually no starting vertex. So we choose one arbitrarily. We choose one arbitrarily, consider all the neighboring edges. And we would actually use the priority queue again to find like the smallest neighboring edge. We want to add that edge to the tree because there's nothing better that we can do. So like, let's say this edge was connected to that. This is the smallest one. Let's say we started here. We're considering this one, and that one. This is the smallest, so we want this edge in the tree. And there's a proof for this, but I really don't know the proof. We just know it works. I usually don't use this algorithm. So you keep doing this until you add n-1 edges, such as this maybe. So those 4 edges form a spanning tree. And it looks like the minimum spanning tree. We keep doing this. We added 4 because there are 5 vertices. And then we get the tree. The other one that I like to do more is Kruskal's algorithm. And we put all the edges in a priority queue. Then we consider the smallest edge out of every single edge in the graph. And then we add it. And if it doesn't form a cycle with the trees, with the existing edges, then we add it to the tree. And we keep repeating that. Okay, well, it's 4:59. I really wish I could have gone over the code for Dijkstra's or Kruskal, but you know what? AMC 10 is actually very fun. So you guys are in for a treat. Tina is here and I'll make her host.
Thanks.
The handout 3 is on the website now. Handout 3 is on the website and handout 4 will be on there soon. Dennis, do you have a question? I'm not too sure if you raised your hand for the phone. Okay, well, thank you so much, guys, for coming today and for staying these 4 weeks. I hope you have a great summer. Yeah, thank you so much. Bye.